Okay. So we're returning to the subject of multithreading. So we touched on many key elements. However, how to adapt your existing executable to multithreading if it has some complications is something that bears a fair amount more effort. So this touches on a few of the topics. Thread safety in general and why it's an issue. An example from potentially reading an input file in multi-threaded mode. And one small new addition about the possibility to optimize the geometry, complicated geometries in parallel. So first, thread safety. Now, you probably have some reasonably complicated code in your application, and you might wonder whether the fact that it's being executed in multiple threads will affect it. If the code just reads a value, does something, writes a value somewhere else, maybe not. But there are times when it could be affected. And one of the times is when it will store a particular value and do something depending on what the value stored was. For example, you might be accumulating some energy, and then if it's more than a certain value, do something. In this case, let's think that you have two threads to do it in the simplest possible multi-threaded case, and that you have this stored value. Why would you have a stored value that's the sum of something? Let's say that it's not the sum of something, and maybe it's something that if you surpass a certain value or whatever. And you have some code which depends on this stored value. So in particular, if the stored value is, let's say, larger than 0, you do one particular thing. If it's otherwise, you do something else, and then you flip. This seems fragile. It is fragile. But let's say that you needed something of this type or something not too different. What will happen? So your first thread will arrive somewhere. You declared the initial value to be 1. It's larger than 0. It'll do this. But at the same time, the second thread will start operating and will reach the same location in the code. It's not clearly defined either to you or to the program whether the first program will have already changed the value of this or not, or the first thread, I should say, when it's been executing. So this is a badly formed program. It is not something that one imagines only in the context of Geant4. Lots of people have been working on programs like this for a significant amount of time, since the 60s, in fact. And there are many ways in which this has been solved. The simplest ones, and the one that we use in a few places in Geant4, only a few, are you utilize a mutex and a lock, where you say, when you're entering a lock, one program can obtain this lock. The others, if thread 1 obtains this lock and thread 2 arrives at it, it will have to wait until thread 1 gives up this lock. So in this case, it will be well defined. If you have a stored value, you will lock, you will read the value of the stored value in thread 1. You will do whatever's needed, then you will store something new into it. And you will get to the point where unlock is called. When unlock is called in thread 1, then the state of this, what's called a mutex, mutual exclusion variable, will change. And then thread 2 will be able to return from its call to the lock and be able to continue and do its own work. So in that case, the value that's been stored here will be well defined. It will have been changed from the original value 1 to -1. And so what it will do is it will do this. It'll take the second if. And then thread 1, if it came back to this function while thread 2 had locked it, would not be able to continue until thread 2 had called unlock and unlock had finished working. And in that case, thread 1 would be able to continue. As you can see, this will slow down the program, but at least if you're using a shared resource, you will get an answer that's well defined, and you will not get, to put it mildly, total rubbish or unexpected results. So there are some uses for things like this. Certainly during initialization, it's needed to be done, and there's There's other things that you can do in order to make sure that things proceed correctly, but this is certainly the simplest. There's another possibility to re-examine why in the first place you wanted to have a value which was shared. Maybe in your program, this was a convenience, and having this value turn into something that's shared between threads was not the right decision. Maybe what you really wanted, what you really should be doing is you should be storing a value, an accumulator value, or whatever it is, that sums only whatever you, or takes into consideration only what you're doing in this particular thread that's running. In that case, you make the variable thread local. This is the way in which it's done in a C++ program. In Geant4, we have G4 thread local. In that case, there's a different memory location that's being utilized for thread 1, and a different memory location that's being utilized for thread 2. And as such, these proceed independently. No lock is needed. They're talking about different things. So recall, in a sequential program, you have a run manager has its own action. Similarly, a tracking manager, its own action. A user stepping manager has its own action. When you have a multi-threaded program, each of these threads will work with a different copy. So if you have complicated code in your user event action that, or in your user tracking action, user stepping action, you might need to review it to make sure that you're not depending on something that you have stored in a common variable, in a variable that's static, and that you make sure that its storage requirements are correct. In Geant4, we need, since I mentioned that the design of Geant4 in the 1990s did not take into consideration multi-threading, we needed to come up with a way in which different classes, some key classes could have both read-only data, which was shared between all the threads, and it could refer to data which was thread private. And for example, let's pretend that the geometry object had some attributes like the size and the position, but then it had some other attributes which were different, needed to be different per thread. And in particular, the sensitive detector is going to be different per thread. You create a sensitive detector in a method called create sensitive detector and field of your user detector construction. Each thread will call it. When each thread calls it and it assigns it to your logical volume has a place which it will refer to in memory, in which it will hold the pointer to the sensitive detector for thread 1, a different place in memory which will hold the pointer to the sensitive detector of thread 2, a different place in memory that will hold the pointer to sensitive detector 3. So you may be thinking the logical volume is shared by all the geometry. It is correct. Yet my sensitive detector is not shared. The fact that this is the case does not need to worry you. We have some a mechanism behind the scenes that does this. In particular, for the sensitive detector, you have the logical volume that can point to 0 or 1 sensitive detector, but this is per thread. Whatever lives in this here is dereferenced by an identity of the thread, and it's so when you ask a logical volume for its sensitive detector, you will get a different answer in thread 1, in thread 2, in thread 3, and so on. Similarly, everything that falls off of these, the hit collection that you will have, the multifunctional detectors, primitive sensitivity, all of these things you will obtain different objects in different threads, and you don't have to take care of assigning them to different threads, because this is done when you create these objects in the right place. For example, in the user detector constructions, create SD between sensitive detector and field method. That also means that that method needs to be thread safe. The second topic, one thing that one can imagine wanting to do in many an application is to read input from an external file. For example, to read input for primary particles. In a sequential application, you just read the input. It's one thread of execution. You don't need to worry about it. In a parallel application, you need to worry about it. If each thread would read the same file, you'd get the same, for example, directions or energies. It's not what you want. Typically, you want to spread it. The primary generator action is a thread local class. So thread 1 and thread 2 will have an instance of this class, an object of this class. So they cannot just blindly, each one open that file, read its values, and utilize them, ignoring the fact that there exists others. The solution, what you would need to do, to actually split the contents of that file so that it's utilized, let's say half of it is utilized by one thread and half of it the other, or it is spread between them, will depend a lot on what it is that you're going to be doing. If you're in a high-energy physics application where you read 10 input particles or even 100 input particles, and they represent 40 eV of energy, which will take, let's say, 30 seconds to simulate, the fact that you're opening that you have to lock a file or to lock a resource, like we showed in the previous, using a mutex, is not going to matter. A lock can be obtained in milliseconds or maybe even microseconds, depending on how well it's implemented, probably microseconds or maybe even less. If you have an application in which your particles represent 3 MeV of energy, and the simulation time is going to be on the order of milliseconds, then it's going to start to become a much bigger issue, and you have to worry about how you undertake it. For the simpler cases, the mutex, looking at the mutex way of handling it, the mutual exclusion locking mechanism, which in Geant4 is implemented in the G4 auto lock class, can provide a first answer, and certainly an answer for the cases where it's not really particularly important. CPU time is not particularly important. So in this case, we can take an example from the event interface file that reads a Pythia input file. The interface has to be a single object shared by all the primary generator actions. And the access to this method, which will generate a primary vertex, can be protected by a mutex. You will have a single instance of your event generator interface class, and it'll be shared by all the different threads. I note that the full detailed example exists in examples extended run an event R05 if you want to go and look at the full thing and how it works. When you actually generate when you first create an object in each thread for this generator action, you will lock so that only one class can come out and generate this object of the HEP-EVT interface. There must only be one of these objects. You're sharing it. So you create a lock, and the fact that the method ends means that this automatic lock will be released. That's why it's simpler. In the previous example, you saw you had to lock and then you had to unlock yourself. Autolock takes care of this. Once it goes out of scope, it will release the resource. So the mutex will be unlocked. Similarly, here in the destructor, you will lock, you will delete this, and set the pointer to null. When you're generating primaries, you call this method, you lock, you ask this resource to generate a primary for you, and no one else can be calling this interface, this method was not originally thread safe. It's just going through the file and it's giving you an output. This is fine if it takes multiple seconds to actually simulate what you get. You have a reasonable number of threads. You're not going to, this locking will happen on the order of microseconds. You don't really, this overhead does not matter. However, let's say you have particles which you're simulating particles with MEV order energy. In that case, things become a bit more time critical. In that case, you might want to read not one, but maybe 100 particles from an input file. If you're sharing the reader again, here, you're sharing it between the different threads. And you're in your action, you can again lock. When you, sorry, in your constructor, you will lock. If the reader doesn't exist, you will create one, and then you create a particle gun and you'll initialize it. Whatever you've created in your constructor, you need to release in your destructor. Again, for safety, you will lock. You will, if someone has created a reader which you would expect would exist, you will delete it and then set the pointer to null. In the actual generate primaries, what you will do is you will check that the reader has been created, you will lock, and you will ask it for an event. And then you will utilize a number of information. You will obtain the momentum from the reader, and you will calculate the remaining information here. And you will note that we created a context here in which you will lock, you will obtain the information, and then you will immediately release the lock. It's as though you've called the unlock method because you're going out of this scope. So the remaining calculations, you will no longer have a lock on this. And another thread could obtain a lock and ask the reader and get another momentum direction very quickly. You don't lock at the start of the function and unlock at the end of the function. You're trying to use the lock in the minimum amount of lines of code once it becomes critical for the performance. In some more, an implementation of the file reader. It's a simple thing. When the input file is opened, when you create it, and close when the object is destroyed. When you get an event, you may wish to obtain. If you have none left, you may wish to obtain 100 of these values and store them. And what you will do is you will only do this if your list is empty. If otherwise, if your list is not empty, you will just pop a value and you will be returning it. That way, what you have done is you will read 100 by 100, and you will try and do something that's more performant. So in general, a mutex does have a performance penalty. So you're trying to utilize it as best you can. And in the case where you have a lot of resources, what you're simulating is small. Take each of these events takes a small amount of time. It may make more sense to split the input file into separate input files and have each thread read from a separate input file. That's obvious, but it may also be that if you have problems in implementing what's done, that's your interim solution, and then you create something that's performant enough for your use case, and have in general, buffering like the MyReader class could still be used to reduce the input-output overhead. It depends a lot on your use case. So this is a more recent addition to Geant4. If you have a very complicated geometry and you're either trying to use things interactively or you're running things in relatively small batches, the fact that your simulation might take a few minutes to initialize could be of something that would be relevant for you. If you're running a program the size of a large HEP detector interactively and it takes 10 minutes to initialize, then you'd rather that you don't have to go for coffee every time you need to make a small run. So one of the ways that we're trying to alleviate it is to allow you to initialize in parallel. There are some things that cannot be done in parallel, but certainly initializing a geometry is something that can be done independently, so long as you have a number of volumes which are contributing to the time that it takes to do the initialization. If you have a few hundred logical volumes, then more than likely you will have a few which have a fair number of daughter volumes, 10s, 50, 10s, better hundreds. If you have more than a couple of volumes that have 1,000 daughter volumes, then you're more than likely to be a candidate for benefiting from this. In release 11.3, it was possible to start using multiple workers to share this initialization work. The voxelization work is done individually per volume anyway. So you share it between, each thread can take a logical volume one by one, and that way you share the work. Since release 11.4 beta, it is on by default. I would expect it to be on by default in the release that happens in December. If you're using 11.3, then you'd simply need, typically in your main program, to ask to obtain the object of the geometry manager and request parallel optimization. And you can request it to voxelize in parallel and also to be verbose to show you the results of what it's doing. It's also possible to ask the optimization to be verbose even without this. And if you see that it's taking a fair amount of time, this would be an option for you. In both cases, in the sequential case in which you are asking it for the verbose output, and it will show you, as Gabriela showed yesterday, these volumes are taking the most CPU time, these volumes create the most memory. If you're seeing that they are reasonably significant CPU time, then this could be of interest. If this is being done in fractions of a second, then you don't care if it's done in parallel or not. Since this is new functionality, if you find it useful, if you run into problems, by all means let us know. It can certainly have a reasonable effect even on a laptop. If it's complicated, it can reduce it from a minute to 10 seconds, which is not a benefit that you mind having. Hopefully in the future, this will happen. We'll be able to do this also with some of the things that are done at functionalization of the physics, but at the moment it's not yet there. So that was the set of topics that I had prepared to complement what was discussed about Geant4 multithreading already. Are there any questions? Maybe it's muted, sorry. Maybe it's not even on.
Okay.
Okay.
If I call abort run on the worker thread, does it abort entire run or for that specific worker thread's run? Or can I control?
I'm not aware of control. Abort run will abort the whole run. However, the timing of when it will abort that, I'm not so sure of. It was something that was raised more recently. I think that events will finish on different threads and then the run will be aborted.
Question from this. Can you explain to someone with experience with scientific computing why Geant4 runs on CPU and not on GPU? We have research based on active and running Geant4 on GPU.
So, very simply put, although simulating different particles is independent and could in principle be run not just by different threads on a CPU, also by different threads on a GPU, the GPU is created to do pretty much the same thing on all of its individual computing elements. When all of the individual computing elements are simply tracing optical rays to the nearest triangle to give you a nice picture, it's easy. When all of them are contributing to doing matrix multiplication operations to do the simulation for machine learning, fantastic. When you want them to simulate completely different types of elements in a complicated geometry of an LHC detector, where you have spheres, cones, cylinders, boxes, twisted tubes, polycones, you can start to see that it's becoming increasingly difficult. And also, if you're undertaking this when you're trying to just generate a picture, then you have some sort of tolerances by which you don't mind something missing, an intersection. It's not, you understand that there will be some approximation, some things will miss each other. When you have a particle that's trying to hit a volume, and if it hits a volume, it's going to leave some energy deposition, and you're trying to make sure that it gives you the same results as a CPU, you have less room for making such approximations and using lower precision, which is one of the things that the GPUs are doing in order to be faster, especially for floating point operations. So although it is something that has been on our horizon for maybe a dozen years, and in which there have been a couple of efforts, some starting about 8 or 10 years ago, and others recently starting 2 or 3 years ago, maybe 4 years ago now. There is no slam dunk solution. There are some specialized codes out there that do it only for medical applications, but they are proprietary. For high energy physics, we started an R&D effort, as I said, a few years ago, aiming at simulation of high energy physics detectors in their complexity. And now it's starting to bear fruit in that the adept prototype is something that has been tested with the full complications of LHC detectors and trying to do what they are doing in a typical run. And we're starting to get results for that. To bring it into a time when it's been part of what would be used in production by hopefully several LHC experiments, that will take some more time to mature. Using it in other fields is an open question. At the moment, what has been targeted is the simulation of electrons, positrons, and gammas, mostly in calorimeters, but it can be used elsewhere. The showering is what makes it more interesting. The complications of the geometry are what takes the most time. But after a fair amount of development effort, we've got to the point where it becomes an interesting proposition to utilize existing GPUs for this purpose. One wouldn't go out and buy a GPU to run Geant4 on at the moment, whatever what your expected use is. So I think that's basically it.
Okay, there is another question by Stefanos. Correct me if I'm wrong, but it seems that there are many approaches to extend the model to MT mode. Some examples use G4 accumulables, others define G4 allocator, others define their own run class. Mutex seems rather complex, but would you recommend Mutexes above all mentioned approaches? Let's assume that we care mainly about the energy deposition in a complex geometry.
So in general, I would stay away from mutexes unless you're forced to utilize this. This is what you do if you need to use a shared resource. If you're only caring about energy deposition and you have an application in which you can use the scoring options which were discussed by Makoto yesterday, the Geant4 scorers already accumulate values between different threads. So you have the ability to obtain this information. If you need per event accumulation, then you might need to use your own hits and create classes which are then written out separately per event. Using mutexes is more for things which you have to share and which you have your own code which already is doing something. I would certainly not try and encourage you to jump in and utilize mutexes for this purpose. The question of using accumulators.
Can I add to this discussion?
Yes, please.
Let's assume that you have 10,000 threads. If each thread will set mutex, maybe one mutex will take a little CPU overhead. But it is more or less clear that your code will be ineffective. We use mutex, we're trying to use mutex only in time of initialization and time when we end the job. At that moment, mutex may be useful. And we're trying to avoid to use it in the middle. We are trying to run within threads independently as much as possible.
Certainly within the toolkit and within user code, mutexes are really an advanced use case for things that you have to do that you need to share. There are other options. There's something called an atomic, which allows you to sum things between different threads in a way that when the operation is happening, let's say you're accumulating something, you can accumulate something between threads and it will be done in a safe way. First, one operation will finish and then another operation will finish. But if it's not necessary, it's better to avoid it. If you're doing things which are complicated, I think, or if you're doing things which accumulate information on one thread, and then at the end of your run, you bring to accumulate more, and you're doing only a very small amount of stuff, as Vladimir suggested, then a mutex would be a reasonable way of doing it. You're only finishing your job. His idea of using 10,000 threads, I think, is rather unrealistic in any context whatsoever. But you can certainly imagine that your CPU in 5 years' time might have 64 threads or 128 threads, especially if things proceed as they are proceeding, or if some architectural changes happen and you get a big grant and you decide to get a very powerful machine, you could maybe even do it today. But even in that case, even in the case you have 64 or 128 threads, if you're doing something that takes a bit of time, then you're going to see a performance decrease if you're using mutexes in the middle of what you're doing.
Great, thank you for elaborating. Thank you.
Welcome.
I don't see other questions. So
maybe we finish this subject and go